Hello, 안녕하세요. My name is INIGO QUILEZ, and I'm a graphics programmer. I've been doing graphics for a long time now, since the 90s, I think, when I joined the demo scene, and we were doing a lot of procedural and 64 kilobyte demos and things like that. Then I joined a virtual reality company to do real-time rendering for about 6 years. And then after that, I joined Pixar, where I was doing offline rendering and films, where I used a lot of the procedural techniques I had learned on the demo scene and applied them to offline rendering. After that, I joined Oculus to do virtual reality again and real-time rendering, where I was in a team that were trying to create films in real time. So that was a very constrained environment because not only was real time, but it was 11 milliseconds rendering budget, because that's the frame rate of the headset, which was 90 frames per second at the time. So just in 11 milliseconds, we had to render two eyes, the left and the right eye, in high resolution. So that was very challenging. And that's where I developed a lot of techniques that I want to share with you today. At the same time, I'm the co-founder of Sh8dertoy, which is this online community of people who are creating shaders and inventing new techniques and sharing them with everyone, for everyone to learn. So I'm very proud of that part of work. And I'm going to be using Sh8dertoy today to show you some of those things I learned about real-time rendering that I think can be useful for indie game development. So I'm not a game developer myself, but I do know that when you are working on a small team and don't have a big budget with a lot of artists or engineers to develop new technologies, you have to work with game engines and simplify your art, or be as smart about your art so you can get the project to finish. Now, I think this is a great opportunity to actually make things that the game engines can normally not do or don't want you to do by default. Many of the game engines are optimized for AAA games with shadows and lighting and photorealism, but there is a lot you can do without any of those things, as you guys know. And I think today I can show you some of those techniques I have developed that can work very well in that context of indie game development that will produce beautiful visuals beyond what a game engine can give you by default. So I'm talking of things like perfect shadows without any artifacts and without using shadow maps, so you don't have to pay all that expensive rendering time, which is great for mobile phones. I'm talking of anti-aliasing without multisampling. I'm talking about perfect texture filtering and things like that that will give you perfectly beautiful pixels on the screen and effects that you couldn't do normally without having to pay a lot of cost. So let's start with something simple. This guy here, he's Henry. This is a character we developed in 2015 for a virtual reality film I was making. Now, Henry was very expensive. This was 2015, the hardware wasn't very powerful, and he was taking 5 milliseconds out of the 10 millisecond budget we had for rendering. So we didn't have much left for the background, the shadows, and the lighting, and all those things. So, because we couldn't afford shadow mapping or shadows, I decided to use drop shadows, which is of course a technique that has been used in games for a long time. However, I decided to make just not a sprite that you splat on the screen, but something that behaved physically correct. So, I replaced Henry with 4 spheres. The point being that once you replace the geometry of polygons with just a sphere, you can do some mathematical analysis on it and develop equations that produce exact ambient occlusion and soft shadows, the same that you would get as if you were ray tracing the whole thing. For example, here, the left side is ray traced and the right side is using these equations to produce exactly the same ambient occlusion. You can see that if I move this separation line left and right, you cannot really tell which one is which. So this is great because now we could have ambient occlusion that is working in real time with just a dot product and a division and a few operations. Now, the same idea of using a sphere and using mathematics to extract exact shadowing could be used to compute shadows from actual light sources. So we could have shadows that not only represent where Henry is, but behave properly. For example, in this sphere here, you can see how as the sphere goes up and down, not only the size of the shadow becomes bigger and smaller, but it's also getting blurrier or sharper. And it's doing it in the proper way. For example, on the right side, the shadow is sharper, while on the left is blurrier. Doing this with a traditional drop shadow based on sprites is difficult. However, with this simple equation, you can get it for free. And actually, implementing this equation is probably faster than fetching the texture and reading all those text cells for splatting the sprite. So besides shadows, another thing I did for Henry was to create analytical and mathematically correct glow. So in this case, there are these balloons floating in the air, and we needed them to be surrounded by glow. Of course, doing glow in a game engine is easy. You just drop a new pass and you blur the image and you add it again, or you add a post-process effect or something like that. But again, we couldn't afford that in the low rendering budget we had. So instead, I decided to put some spheres around the balloons. These are mathematical spheres. They don't actually have polygons, or they don't exist in the game engine. These spheres are only mathematical concepts inside the shader that is rendering the scene. But with that mathematical representation, I can do some analytic equations and resolve the perfect glow that would be produced if those spheres were full of light. Again, this equation is super simple to evaluate and produces beautiful glow. No multiple render passes, no reading from textures, and nothing expensive. This runs full frame rate in any hardware. So let me show you just one more frame that shows how this glow looks like. Another thing that this glow technique can do is that it can be used for colorizing the space. You know, normally you do color grading on your game or your film to bring the mood and the style you want for it. But when you are in 3D and in virtual reality, you probably want to do this grading in 3D space, not just as a 2D path to the whole image. So in this case, by placing spheres around the environment, I was able to use this mathematical glow technique to tint the environment in different colors and add different gradients, which helped me bring a very cartoony and lovely style to the scene without having to do complex volumetric rendering. So as you can see, spheres are very useful. Because they have a very simple mathematical equation, you can use them in shaders to do all sorts of things. So this is an example where by just using a square root and a few multiplications, you can do perfect motion blur of a sphere. Now, in the philosophy of adapting your technology to the art and the art to the technology, you could make a game where all the characters are just spheres. Why not? And in that case, if that was your choice, you could produce a game that has perfect shadows, as we saw, perfect ambient occlusion, as we saw, that glows beautifully, and have perfect motion blur, all at 120 frames per second or 30 or 60 or whatever. No constraints. So that's great. So by now you might be thinking, well, but my game is not made of spheres, and I don't want to replace everything by spheres, or I don't think it can. So what do I do? Well, it's okay. We have many other primitives that do accept mathematical representation and have analytical and perfect ambient occlusion and shadows and all these things. For example, we can use ellipsoids, we can use capsules, we can use boxes, and in this case, you can see that we can compute the perfect ambient occlusion of a box, just as if we were ray tracing it. And I might argue that maybe not many games are made of spheres, but I bet a lot of games and successful games are made of just cubes. I can think of a couple. And then of course you can combine all these techniques together and do things that you cannot just do with simple primitives. For example, this is a shader in 섀더토이닷컴 that I made recently, where we have an hexagonal field that goes to infinity and has beautiful lighting. So let me go here and show you how I can replace the lighting quickly to show you the ambient occlusion pass. Now, this looks pretty good. Actually, it's perfect ambient occlusion. It's equivalent of having had all this geometry in a path tracer, you know, in Arnold or in Maya or in some renderer, and spending a few minutes rendering the image. So this is perfect ambient occlusion. However, it's happening in real time because I'm using the equations of analytic ambient occlusion for a box, or rather of a quad. As you can see, all it takes really is just a few normalizations, a few cross products, and some inverse cosine functions. Now, this sounds like a very expensive thing, but if you consider this versus casting rays and doing temporal reprojection and bilateral filtering and all those things, this is really, really cheap. And of course, you don't need to cast occlusion from any quad to any other quad. You can just pick the ones which are near the point you are shading and only use 12 or 20 quads to cast your occlusion. So just to finish this part of my talk, I will say the same thing again because I guess there's a point I want to make, which is that the same way that you guys usually choose your art style based on the budget you have, on the engine you are using, on the expertise you have, and things like that, you could also make a game where you choose your art style to be good for this mathematical representation of geometry that allows you to have perfect pictures. Basically, I'm saying you could make a game that looks perfect in that it has the same motion blur, shadows, and ambient occlusion that a professional movie would have, but you can do it in real time if you choose your art style to be made of sphere, hexagons, boxes, and things like that, that allows you to use all these mathematical techniques I just showed you. So to that end, feel free to go to Shadertoy and explore all the shaders that people are creating, where many of them are showing these techniques, and you can basically use the code. You can also go to my website where I explain many of these techniques, and I even explain how to derive them in case you want to derive your own mathematical expressions that will allow you to do perfect lighting and things like that. So yeah, there is that. All right, now I want to talk to you about something different. I'm going to talk about some texture filtering techniques that you can use in any game, in any context. You don't have to sacrifice your art style or change it. This is just a technique that you can use anywhere. So I have noticed that many games are using kind of pixel art in that they try to replicate the old school art style where you have a very few pixels. So they create textures where you see the pixels of your characters or your sprites and so on. And the problem is when you try to bring these textures to your 3D engine and you are using the default bilinear filtering of textures, then what you get is this blurry image that you see at the top here, where naturally the texels of the texture have been blended together by the engine in an attempt to smooth out the otherwise pixelated images. But in this case, it is pixels what we want. So many developers would go ahead and disable bilinear filtering in their engine and use point sampling or nearest filtering. And then what you get is the picture on the bottom side here, where you do see pixels, so that's great, but you also have this flickering of the image. As the texture moves across the screen, you have this uneven amount of pixels that are covered by a single texel. And as that quantity is not constant and stable, then the image is performing this weird flickering. Now, most game developers will just stop here and deal with this artifact. But however, the technique that you can use to fix it is relatively easy. First of all, let me show you what it looks like when the fix is applied. Now, if you look at the top image again, you can see that you can still see the texels of the texture, but the animation is smooth now, especially if you compare it to the one at the bottom. Let me disable it again and enable it again. So the shader is pretty simple. This line of code here would be your regular texture sampling. That would be the thing you would see if you open the shader in Unity or Unreal Engine or whatever. And these few lines of code here, which is like 5 or 6 lines of code, is all you need in order to fix the problem. It's a simple fix. It doesn't take much computation, especially considering that the texture is going to be fetched right after these arithmetic operations. So I don't think there is any reason not to use it, and the quality is pretty good. Besides just fixing translations and animations like that, it will also fix rotations and basically any movement of the sprite across the screen. So it's pretty good. Another technique that I want to show you that solves aliasing is one that you can apply when you are using sine and cosine waves. So these are things that you might be using already on your procedural shaders if you are trying to simulate water, like an ocean or a river or a waterfall, or actually many other things can be also simulated by using sine and cosine waves. So if you are that kind of game developer and you are using cosine waves, you might have seen problems where distant pixels, like the faraway parts of the ocean or the river, are shimmering and aliasing. That happens because the waves themselves are going up and down, the sine waves are doing their thing very quickly because of perspective projection, right? So a wave might be very big on the screen when it's close to the camera, but as the ocean goes farther away from the camera, then all those waves quickly compress into very few pixels of the screen, again, because of projection. So in that case, what happens is that you have the waves oscillating quicker than you can sample them. Rendering them into pixels, that's sampling them. You are taking a measurement of that wave in order to put a color or something on the screen. So when those oscillations happen quicker than you can sample them, you get aliasing. This is called the Nyquist theorem. So we can solve it in many ways, but one way I developed is that you can band limit or remove some of those oscillations as you detect that they are happening far from camera. So I have an article that you can read where you can see what the math is behind it. But if you don't, that's fine. You can just copy the shader, actually. It's in Ŝadotoy. This is the URL. And the technique is super simple. It just uses a few instructions to kind of attenuate and remove the cosine waves that are creating the problem. And as a consequence, you can see that the top image is beautiful and smooth, while the bottom one, where we are not applying the technique, the image is very aliased. Again, it doesn't need super sampling, multisampling, or anything at all. It can be dynamic, so the waves can be moving, something that you cannot do with textures and bit mapping. So there is no reason not to use it, I think. It's pretty cool, and I hope it helps you. And on that note, this is the end of my talk. I hope you got something useful from it. I know there is a lot of things to process, but go to my website or to Ŝadotoy and learn what other people are doing about these techniques, because I think they can be very useful for game development. And yeah, I hope something of this was useful to you. Thank you so much for listening, and have a good day.